We have been working on this concept of a mean squared error, where we define some difference between what we observed minus what we predicted squared. And we really haven't given justification about this, other than the fact that it's easy to take derivatives of squares. Why are we minimizing mean squared error? And the answer comes from a statistical representation of the problem, and that is maximum likelihood. And basically, the story of maximum likelihood is that you have a model that describes how the things that you're measuring are related to the things that you're trying to estimate. And I'm going to introduce the notation that we're going to use to describe that. So something that you're measuring, I'm going to put two circles around it. You measure x. You believe that x is going to influence, using a conditional probability, another thing that you're measuring, y. And there's this hidden variable, which is the random variable w, that also influences what you're measuring, y. And the single circle means I don't know what this is. I'm going to have to estimate it. The double circle means that I'm measuring that. The arrows refer to conditionals of the probability function. So what this implies is that there's some probability of y given x and w. So what is this probability? Well, in our models that we've been describing, probability of y given x and w is that, well, probably it's a normal distribution with the mean w transpose x and some variance sigma squared. So suppose this is my model. It says that when I see an x, if I multiply it by w, I'm going to get y, but it is not going to be exactly y. It's going to, on average, be y, and it's going to have some variance sigma squared. So such a thing, of course, comes out of a model that says my estimate, y, at trial n, is w transpose x at n plus some noise epsilon at that trial, where epsilon is normally distributed with mean 0 and variance sigma squared. And so then, if this was the case, then the probability of y given x and w becomes this normal distribution. And what is this normal distribution? It's 2 pi sigma squared to the 1/2 times this exponential minus 1 over 2 sigma squared y minus w transpose x squared. So this w transpose x tells me the mean of my distribution, and sigma squared, which is the noise in my the variance of my noise, tells me about the width of that distribution. So what I did is to try to write the problem of regression using a probabilistic approach, where I measure some variable x, I measure some variable y, and I want to know this w. And I believe what I'm measuring is related to x and w using this model that you see here, this probability distribution. So what is maximum likelihood? Maximum likelihood is the idea is that you begin with a hypothesis regarding the probabilistic model that relates things that you can measure to the things that you want to estimate. So basically, this model, the model should be a description of how you believe your data was generated. And this is called a generative model. So what does that mean? So this here is a generative model. Why? Because it says if I give you X and there exists some W, using this probability distribution, I can give you some data. So I can give you Y if you give me X and W. And using this generative model, I can generate for you data for which then you can fit your model and you can see how it works. So the first step in maximum likelihood is we begin with a hypothesis regarding the probabilistic model that relates things that you can measure to things that you want to estimate. Then the second step is you find the parameters of the model that maximize the likelihood that the data that you measured was generated by your model. So if you have some data points, so here's our data points. Y1, Y2, Yn. So we want to maximize the likelihood of having actually observed these data points. So what does that mean? We have to describe the joint probability of Y1 being equal to my estimate, Y2 being equal to my estimate, given that I observed X1, X2, Xn, and I have some weights W. So this is the probability that this says how likely is it that I have this data that I have here, given that I have some X's that I experienced and I have some W. So the idea is you want to find this unknown W that maximizes the likelihood of having seen this data. You saw some data, you measured some data. You want to find the parameter W that maximizes the likelihood of having seen that data. And of course this requires a conditional probability. And we have that. I don't know what's going on here. All right, let's try again. Oh, God. I don't know. Okay, so this probability, what is it? So this probability is a joint probability. And a joint probability, we can divide it up into individual components based on, let's see if I can move it here.
Minimize, maximize,
All right, so maybe, okay, this seems to work now. Okay, good. So, okay, we can write this probability as the following: the probability of the first data point being equal to what I observed, given that, I'm sorry, let me fix this. This is not correct. So let me write this correctly. Okay. So we want to maximize the probability of the thing that we observed, the y being equal to what we observed, the second one being equal to what we observed, so on. And so the probability of y being equal to the first point that we observed, given that x is this first point, and w times the probability of y being equal to the second point that we observed, given x2 and w, times all these other probabilities, which is equal to multiplication of all of these probabilities, I is equal to 1 to n, times the probability of y is equal to the first, second, third, all those points, given xi. Is the internet off on this computer?
Yeah.
Okay. So this is called a likelihood. Just to see what it means the likelihood is the probability of all the data points that we observed, given all the things, x's that we have, and this parameter w. And the idea is, maximum likelihood is to find the w that maximizes this quantity. So what we did, let me just summarize what we did. We said we want to write what's the probability of having observed this data. That probability can be written as the conditional probability that says, here's my data, here's my x's, here's my unknown w. And when I want to maximize the likelihood of observing this data, I am going to find the parameter w that makes this joint probability as large as possible. That's called maximum likelihood. What's the parameter value that maximizes the likelihood of the data that you actually have? Let me stop to see if you have a question about that. I'm going to go over the details of this in a minute, but that's the basic idea. So maximum likelihood starts with a probabilistic model that relates the things that you measured to the things you're trying to estimate. And maximum likelihood is a process by which you make it most likely that the data that you saw comes from the model that you hypothesized. So let's do some examples of this. Instead of doing it for somewhat complicated thing like regression, let's do it for something simpler. So suppose you draw n numbers from a uniform distribution. So what we have is we have some probability of the data being over some range 0 to a, and we think that our probability is uniform, so it looks like this. So we can write the probability of y is equal to yi given some parameter a, then that's just equal to 1 over a, right? The probability of any number in this range for y I being in this range, and 0 otherwise. So what's the likelihood of the parameter a? That's equal to all my data points, the probability of those guys, probability of y is equal to yi just 1 over a raised to the power n. This is the case if a is bigger than or equal to the largest y that I have, and 0 has to be less than or equal to the smallest y that I have. So if this is the case, if a is bigger than the or equal to the largest y that I have, then this is the likelihood. So now the question is, what is the maximum likelihood estimate of a? How big should it be? Well, we want to find a that maximizes this likelihood. Here it is. So you want to find an a that maximizes this quantity. Well, the largest number that I can get for my likelihood is for the condition where a is basically equal to the maximum size of my data. So you want to take a to be as big as the biggest number that you have, but no bigger. That will give you a parameter that maximizes the likelihood. So look what I did. I said I have some data points that come from a uniform distribution. That uniform distribution is described by a parameter a. I don't know what this parameter is. I want to know what's the maximum likelihood estimate of a. I find the likelihood of a, which is just a multiplication of each probability. It's 1 over a to the power n, where n is number of data points. So what is the maximum likelihood parameter for a? It's the maximum value of a. Okay. Let's do another example. Let's try a exponential distribution. Suppose that my data p of y given a is distributed as follows. What?
Reset my computer.
Sure. Why don't we do that? Let's pause for a second, and the computer's not working so well, so let's see if we can. All right. Hopefully things will be better. Let's see if it works. All right. So we've been considering the case where we have some data that came from an exponential distribution. So here's our data, here's our probability. It's like something like this. And we'd like to know this parameter a of this probability distribution. So likelihood. The likelihood is the probability of our first data point, our second data point, and so forth, given this parameter a, which is equal to the joint probability, I is equal to 1 to n, of 1 over a e to the minus 1 over a y of I, which is equal to 1 over a raised to the power n times an exponential where we now have a sum of 1 over a times yi. So we want to find a that maximizes this expression, and a typical approach is to look at the log of it, and so this is going to become our log likelihood. So the natural log of the likelihood of a, let's see what that looks like. So we're going to take the natural log of this quantity here, this quantity. So natural log of 1, first of all, natural log of something times something else is natural log of the first plus the natural log of the second. So natural log of this first element here is going to become natural log of 1 over a to the n plus natural log of an exponential is just going to be the sum of minus 1 over a yi. So this first term, that's equal to, you have a log of something divided by something else, and that's going to become log of the first minus the log of the second. Log of 1 is 0, so we get minus natural log of a to the n, and then I have the second term minus 1 over a times the sum of y over I, and I have n of these. So this is equal to minus n natural log of a minus 1 over a times the sum of yi. So what I want to know is, what is the parameter a that maximizes the likelihood? So what that means is that I need to find the derivative of this log, derivative of the log with respect to the parameter that I'm looking for, and maximize it. So if I maximize the log likelihood, this derivative will be 0. So what is the derivative here? So derivative of the first term, derivative of a natural log, is the reciprocal of the coefficient inside of it. So this is going to be minus n divided by a, plus you're going to have the derivative of this term here with respect to a. It's going to be plus 1 over a squared times the sum of y over I, y of I. So when this derivative is equal to 0, then that's when a is maximizing the log likelihood. So I'm going to set that equal to 0 and solve for a. And what I'm going to get is minus n plus 1 over a sum of yi is equal to 0, which means that the maximum likelihood estimate of a is equal to 1 over n times the sum of yi. So the parameter a in an exponential distribution can be estimated using this procedure that I just showed you. All right, let's try a normal distribution. So we have some data, and we want to maximize this joint probability. So probability of any particular data point, probability of it being equal to some particular data point yi, is described by some probability that has a mean mu and some variance sigma squared. And since we're saying this is normal, here's what it's going to look like. 1 over 2 pi times sigma squared 1/2 times the exponent of 1 over 2 sigma squared, the data point that I have, minus this mean that I expect. So this is how my data is going to be distributed. What I want to know is that what's the maximum likelihood of my parameter mu and my variance sigma squared, given that I have some data that I want to fit, y's that I've seen. So we're going to write the likelihood of the parameter mu and the parameter sigma squared. So that likelihood is going to be the joint probability of every one of my data points, so the multiplication of my probabilities. These are the things that I'm going to multiply. And so I'm going to have to keep track of each data point, 2 pi sigma squared 1/2 exponential so that's my joint probability. So if I multiply this through, what I get is, on the left side I have 2 pi sigma squared raised to the power of n over 2 times an exponential minus 1 over 2 sigma squared times the sum of the exponents. So what we typically do, because we have an exponential here, instead of maximizing the likelihood, we maximize the log of the likelihood. So we're going to take the log of this function. What is it going to look like? It's going to be minus n over 2 times the log of the denominator plus this term on the right, which is going to be a negative sign in front of it. Because it's going to be the term inside. So that's our log likelihood. And we want to find the parameters that maximize our log likelihood. What are the parameters here? They are, this likelihood is a function of two parameters, right? The mean and the variance. Okay, so we want to find the mean and the variance that maximize the likelihood of seeing that data. So let's try this. Let me further simplify this. So this is equal to minus n over 2 times log of 2 pi plus log of sigma squared minus the rest of this term. So you notice that the likelihood is proportional to the sum of squares. So the likelihood that we're trying to maximize has the sum of squares in it. And we're going to see later that in a probabilistic model of regression, that's what we are really doing. We are maximizing the likelihood, which means we're going to have sum of squared errors in there. So squaring the errors between what we observe and what we predict leads to the regression equation that we saw before. So we're going to be able to derive the same result from maximum likelihood. So let's continue with our current issue, which is to find the parameters, the mean and the variance that maximize the likelihood. So what we do is that we take the derivative of our log likelihood with respect to the first parameter, which is the mean of my distribution. So that's this term here. So when I take the derivative with respect to mu, what I get is on the front, I get minus 1 over sigma squared, because this is squared here. So then I get a sum of mu yi minus mu times the derivative of what's inside of that, which is minus 1. So I set that equal to 0, and I solve for my unknown, which is mu. So sum of yi is, of course, n times mu, and so mu maximum likelihood is 1 over n times sum of yi. This is what we call the mean. Do you have any questions about this so far? So what did I do? I wrote the likelihood, joint probability of the data. I found the log of the likelihood. I got rid of the exponential. Then I found the derivative, because what I want to do is find the parameter mu that maximizes the likelihood. Set my derivative equal to 0, and here's my maximum likelihood estimate of the mean. So when you take your data and you divide it by the number of data points, you say that's my mean, that's your maximum likelihood of the mean, under the assumption that the data was distributed normally. Okay, what's your estimate of variance? Take the derivative of the log with respect to sigma. So here's one of the terms that has a sigma in it, and I'm going to get minus n over 2 times 2 times 1 over sigma. That's the derivative of log of sigma squared. and then I'm going to have this term here, minus 1 over 2 sigma squared is derivative with respect to sigma. It's minus 1/2 times a minus 2 times 1 over sigma cubed times the rest of my equation, which doesn't have a sigma in the rest. So let's simplify this a little bit. So I get a minus n over sigma plus 1 over sigma cubed times the sum. I set that equal to 0, and I solve for sigma squared. So the sigma cubed and sigma, the sigma goes away. I get sigma squared maximum likelihood is equal to 1 over n times the sum of my data minus my estimate of the mean squared. So this is the maximum likelihood estimate of variance. So in your work, you will probably plot data, and then you will say, I'm going to plot the mean and the standard error of the mean, SEM. So what is this SEM? What is this SEM that we're plotting? And what that is, SEM is your confidence about your estimate of the mean. So let me show you what that is. So when you make an estimate of the mean, you take your data, divide it by number of data points, you say that's my mean. But then you also plot an SEM. And the meaning of SEM is that that's your confidence about the mean. And typically what you do is you take your variance of your data and you divide by the square root of the number of points that you have, right? So why is that? Why is that your confidence? Let me show you why. So what we want to know is what is the variance of your estimate of the maximum likelihood. So when you take your data and you find this mean, what is your variance of that mean? That's your uncertainty about the mean. So what is that? So that variance, so here's our equation of the mean, right? 1 over n sum of yi. What's the variance? What's the variance of this equation? Where y is your random variable. Well, variance of this is going to be 1 over n squared times the sum of variance of yi, which is equal to 1 over n squared. Each y has variance described by my maximum likelihood estimate, sigma squared. So that becomes, I have n of these, so n divided by n squared becomes 1 over n times sigma squared. So when we say standard error of the mean, we mean the square root of the variance of the mean, which is going to be the square root of the sigma squared ml divided by the square root of n, which is sigma ml divided by square root of n. So you see that as your number of data points increases, your confidence of the mean increases. The standard error decreases. So let me stop to see if you have any questions about this. Does it make sense? Yeah.
So how would this work for an exponential distribution? Would you have similar?
You would have to have a description of the variance of that distribution and the relationship between the mean and that variance, and that would give you a different standard error, right? Yeah.
So if we think that the distribution of data is not a normal distribution, we can't use SEM.
Right, exactly. You could use SEM, but not this.
Yeah.
Right. SEM is a description of confidence of the mean, and this is how you derive it, right? It's based on your estimate of the variance of your mean. What that means is that if you had taken your data multiple times from the same system that generated it, what would be the variance in your estimate of the mean? This is how the results would be. So if your estimate of the mean comes from 5 data points, your uncertainty is large. If your estimate comes from 50 data points, then your uncertainty gets smaller. Okay. Great. All right. So the second half of our lecture is about applying some of this maximum likelihood to the problems that we've been considering. So, we've been writing equations that say the things that we observe depend on x based on some linear model plus some noise. And what that means is that there are things that you can measure, x, that produce other things that you can measure, y, that depend on some unknown, w. And we believe that our probability distribution associated with what we measure, p of y, given x and w, is described by a normal that has a mean, w transpose x, and a variance associated with variance of this noise variable, epsilon. So we want to now approach the problem, find w that maximizes likelihood of data y1, y2, up to yn. So let's do this problem of maximum likelihood so that it best fits the data that we actually have. So the probability of y is equal to y1, y is equal to y2, yn, given x1, x2, xn, and our parameter w, that's equal to, this joint probability can be written as the probability of y is equal to the first data point, second data point, etc., given xi and w and sigma squared. Sorry, I forgot to put sigma squared here. Those are the unknowns that we have. These w and sigma squared are the parameters of our model. So this is equal to our normal distribution multiplied across all the data. Okay, so we want to maximize this quantity. We want to find the sigma, which is unknown, and the w, which is unknown, that maximizes this quantity for our n data points. So what we do is that we find the log of our likelihood. So why is it that I can maximize the log of the likelihood, not just the likelihood? Well, because log is an increasing function. So if you maximize the log, you're also maximizing the likelihood. All right, so we want to find the log of this quantity. So first of all, we have this sum in the front, which means we're going to get n of whatever is inside of it. So I'm going to put an n here, and then I'm going to have a sum that I'm going to add up. So I'm going to have n of these terms here. So that's going to be n times, actually, I think it'd be easier if I just multiply it out. So let me do that. So let me take another, instead of having a shortcut, let's just actually multiply this through. So this is going to be equal to 2 pi sigma squared n over 2 times the exponential of 1 over 2 sigma squared times the sum of y over y of I minus w transpose x of I squared. And here's the key thing here. You see that this sum is the sum of squared errors. So that my likelihood is a function of the sum of squared errors. And we're going to see that by maximizing the log likelihood, we are minimizing the squared errors. So this sum, of course, is the quantity y minus xw transpose y minus xw. Okay, let's take the log of the likelihood. All right, so I have a ratio here. So when I take the log of that, I get minus n over 2 log of 2 pi sigma squared. In the second term, I get the log of this exponential, which is just the inside of the exponential, 1 over 2 sigma squared times the sum of, I'm going to write it in the matrix form. Okay, that's my log of the likelihood. So let me multiply it through. Okay. So I want to find the parameters w and sigma that maximize the log of the likelihood. So the way I do that is take the derivative of this log with respect to the parameter w that I'm looking for. So log likelihood is a scalar. This is a scalar quantity, and I'm going to find the parameter w that maximizes the scalar quantity. So I'm going to be taking derivatives with respect to a vector w. And what am I going to get? A vector plus another vector. Set that equal to 0, and I get the maximum likelihood estimate to be our normal equation. So when we were minimizing the squared error, if we assume that our data is generated by a Gaussian noise model, then the maximum likelihood estimate of W is the estimate that minimizes the squared error. So under a Gaussian estimation, under a Gaussian hypothesis about how our data is generated, minimizing the squared error is the same as maximizing the likelihood. Okay. Let's find the variance. Let's find the variance. So remember, we have two parameters. Whoa. We have two parameters in our data. We have this parameter W, and we have this parameter sigma squared. Why? Because our model says our data is generated by a linear description of X and W, and there's some noise that we have. And this noise is distributed with mean 0 and variance sigma squared. So we have to specify now what is the noise. What is the noise in our model? So then what I do is that I find the derivative of my log likelihood with respect to my noise. Okay. So I need to find the derivative here now with respect to sigma. So what do I have? I have minus n over 2. And then I have derivative of the log, which has a 2 inside of it, and 1 over sigma. Minus, I have this term here, which is 1 over 2 times a minus 2 times 1 over sigma cubed times the data, which is the sum of y over y of I minus w transpose xi squared. Set this equal to 0. Solve for sigma that I'm looking for. So that's minus n plus 1 over sigma squared times the sum is equal to 0. So my estimate of the variance, maximum likelihood estimate, is 1 over n times the sum of my squared errors. Okay. Let's take a different kind of problem now. So, to motivate us, I forgot to tell you guys, the text, so we're now starting on the textbook, and this is the material that I'm going to be talking, that I've been telling you about, is chapters, I forgot to mention this, chapter 4.1 to 4.5. That's what we're going to be covering. That's what we have been covering in the lecture. Okay, so let me give you an example that will motivate us to go toward a biological consideration. So suppose that you go hiking and you're worried about getting lost, so you buy 2 different GPSs to go with you. One of them uses US satellites, the other one uses European satellites. Suppose you have these 2 GPSs, and what you're going to do is that you're going to look at the 2 GPSs and you're going to try to figure out where you are by combining the information from these 2 measurements. So we want to use maximum likelihood to do that. And once we figure this out, then what we're going to do is that we're going to look at an experiment that looked at how people integrated the things that they felt with the things that they saw. So they're going to see an object, gives them some information about what the object is, how big it is. Then they're going to feel the object. That's also going to give them information about it. Then they're going to combine these 2 pieces of information to form an estimate. And what the experiment that I'm going to show you did is to say, did the brain use a maximum likelihood estimate to come up with its belief about what was out there? To motivate us, we're going to do the same thing, but first we're going to start with a simpler experiment where we have 2 measurements. Measurement A, GPS. Measurement B, another GPS. They tell me something about where I am. I want to combine the 2 to get an estimate of where I am. And the idea is that the way you combine these 2 estimates is based on the ratio of the noises in the 2 estimates. If one of these GPSs has greater noise than the other, then you want to weigh the information that comes from the noisier one by the reciprocal of that noise, the variance of that noise. So the less confident you are about a measurement, you want to weigh it less as you compare it to another measurement. Then you want to combine the two. So we're going to do this mathematically and see how we can solve the problem. Okay, so let's begin with a generative model. You are at a particular location, X. You're trying to estimate where you're located. You believe that GPS A measures this location, and there's this other GPS B that also measures this location. And you want to know, so where am I, given that I have these two GPSs? So we're going to write the problem as follows. You measure something we call Y, and it's made up of YA and YB. So since you're on Earth, you have a two-dimensional measure, so this is a 4x1 vector. So one GPS tells you where you are, say that's a 2x1, another GPS tells you where you are, that's another 2x1, and together you have this measurement, Y. You believe that this measurement is related to your actual position using this model. So X, your actual position is a 2x1, and you believe that these GPSs are not biased. So what that means is that this 4x2 matrix, you believe, looks like this. Is an identity matrix 2x2 and an identity matrix 2x2. So you believe that these GPSs are an unbiased measure of where you are. However, there's noise in them, this epsilon here. And this epsilon, and what is this epsilon here? What's the size of it? It's a 4x1. And so you believe it's normally distributed with some mean 0 and variance r. And what is this r? R is a 4x4. And it's going to have some noise for the A, for the first GPS, some noise for the B, and then 0 covariances between them. Or this is a 2x2. Okay, so let me stop for a second to see if you have any questions about how I set up the problem. So let me go over it one more time. So you make a measurement. It's composed of two vectors. One is one GPS, the other vector is the other GPS. These tell you where you are. You believe that what you measure is related to where you are based on some relationship that you think is unbiased. You don't think these GPSs are going to add anything or subtract anything on average from where you are. So the C matrix, which is a 4x2, is made up of two identity matrices. However, what you're seeing isn't just some noise-free measure, but there is some corruption due to noise. That noise has 0 mean and variance r, where each of these variances are the variances of those instruments, RA and RB. So what I want to know is that what's the maximum likelihood estimate of X? So we need to write the probability distributions. The probability of Y by itself, you can look at this equation here. The probability of Y is a normal that has a mean Cx and it has a variance associated with this equation. So variance of this is C variance of X times C transpose plus R. On the other hand, what we're interested in is the likelihood. Likelihood is probability of Y given X. That's what we're trying to maximize. So what's the probability of Y given X? That is a normal with a mean Cx and a variance of this equation given X. So if X is no longer a random variable, the variance is just the variance of epsilon, which is R. Let me stop for a second, see if you understood that. So what I wrote is the distribution of Y and the distribution of Y given X. The conditional distribution has the same mean as this, but its variance is based on this condition, which means that X is no longer a random variable. If X is not a random variable, X has no variance, which means the only variance is epsilon, which is R. So this is my likelihood. What I want to do is find the parameters that maximize my likelihood. So let's write this down. Probability y given x is a normal distribution with mean Cx and variance r. So let's write this. So let me just write it down below here. So we have a vector of size 4 and a matrix that has a determinant represented this way. So this is the normal distribution. The conditional distribution has a mean Cx, here it is, its mean is Cx, and it has a variance r, which weighs the exponent and goes in the denominator. So to find the parameters that maximize the likelihood, we find the log of the likelihood, which is the first term minus 1/2 times the log of 2 pi raised to the power 4 plus the log of the determinant of r, and then the second term, log of this exponential, which is minus 1/2 y minus cx transpose r minus 1 y minus cx. Okay, so that's equal to this first term minus 1/2. I'm going to multiply the second term, y transpose r minus 1 y minus 2 times x transpose c transpose r minus 1 y plus x transpose c transpose r minus 1 cx. Do you mind closing the door? Thank you so much. Okay, so now where am I located? So what is x? That's what I want to find. You know, where am I? I want to find the x that maximizes the log of likelihood. So x ml is the maximum argmax of the log of this likelihood. So for me to find it, I want to find the derivative of the log with respect to where I am. And so here it is. There's one term here, there's another term here. So the derivative of that with respect to x becomes minus 1/2 times minus 2 c transpose r minus 1 y plus 2 times c transpose r minus 1 cx. I set that equal to 0. My maximum likelihood estimate of where I am is going to be c transpose r minus 1 c minus 1 c transpose r minus 1 y. So this is what I measured. The two GPSs gave me y, and you see that the rest of it is, I know it. If I knew the noises associated with each GPS, I would get my maximum likelihood estimate. So I want to break this down for you, this equation, break it down for you so we can understand what is it doing. Because that's going to be an important consideration for where we're going to go. So this is our maximum likelihood estimate. So let's begin with r minus 1. What is r minus 1? So r minus 1 is the variance of the noises. It's the noise in the first GPS, inverse of that, and noise in the second GPS. That's the inverse of that. And what was C? C was identity matrix 2 by 2, identity matrix 2 by 2. That's how we define C. So when we say C transpose R minus 1, this term here, C transpose R minus 1, this transpose this, what is that? That's just, you know, this I in the identity matrix 2 by 2, identity matrix 2 by 2 times R minus 1, which is equal to a vector RA minus 1, RB minus 1. So when I say now C transpose R minus 1C, so I'm going to multiply this by my C matrix here. It's this times the first identity matrix plus this times the second identity matrix. So that becomes inverse of the first noise variance plus inverse of the second noise variance. That's the C transpose C. Sorry, C transpose R minus 1C. So when I write my maximum likelihood estimate, what that means is that I have this term, inverse, times C transpose R minus 1 times Y, which is the first noise inverted times my measurement from the first GPS plus the second noise times the measurement times the second GPS. So see what this is doing. It's saying that take your measurement from the first GPS, weigh it by the inverse of the noise, add it to the measurement from the second GPS, weighted by the inverse of the noise, and divide it by the sum of the noises. Right? So it's a weighted combination of the two. So when you have two measurements, each corrupted by noise, the maximum likelihood estimate that combines the two measurements is the weighted average, where the weight is the inverse of the noise. Okay, so this now gives us the experiment that I want to tell you about. So the experiment was published in 2002. And it was Ernst and Banks, 2002 Nature paper. Now here's the idea. The idea was they asked individuals to feel an object, and this object had a certain length. And they asked them to also look at the object, and it was a virtual reality. They saw this object. So with vision, they get an estimate of its size. With their hand, they get an estimate of their size. Now, they are asked to tell, using a psychometric function, comparison, what is the length of the object. So estimate the length of the object by combining two of the sensors that you have, proprioception and vision. It's just like our GPS problem. You have two measurements. Each have noise. So your vision is presumably lower noise than your proprioception. So when you feel something and you see something, when you combine the two, you should get an estimate that will weigh what you saw with what you felt based on the variances of each one of those. And that's what that paper was about, was to first estimate what is the noise in what you see, what is the noise in what you feel. Now ask people to estimate things so that they have to combine these two sensors. And when they did it, they demonstrated that their combined estimate was the maximum likelihood estimate. That's the idea. So let me show you what they did. What they did is that the height of the object was YH through haptic sense or proprioception. The height of the object was seen visually, YV. So this is what the person measured. They saw something, YV. They felt something, YH, with their hand. We can write that Y is equal to CX plus epsilon, where C is a 1 is a 1-1 vector, and epsilon is a normal with variance R, where R is a matrix sigma squared h, that's your haptic noise, sigma squared v, that's your visual noise. And they estimated these things from an experiment, a psychophysical experiment. Now they said if your behavior is maximum likelihood, what you should do is that you should take what you feel with your hand and weigh it based on the noise of your haptic sensation, your proprioception, inverted, plus the inverse of the noise of what you see, that's the weight of what you see, and then divided by the sum of the noises. And indeed, they saw that that's what people were doing. So I want to tell you that you see a paper in Nature and you think, oh my God, they must have done they must have sent a rocket to the moon and set up a microscope there to measure something. But that is not true. Sometimes that's true, but oftentimes it is because of ability to think mathematically and do experiments that test genuine mathematical hypotheses. So this was not a difficult experiment, right? This was not microscopy on the moon. This was a simple experiment that followed a mathematically described idea. And this is often what sets apart these kinds of papers. Okay, so we're not done. There's one more important element here that I haven't told you about. And that has to do with the concept of variance of my estimate. So remember that when we did our maximum likelihood estimate here, we said that there is, this term here, R, that was the variance. And so when you make an estimate of your maximum likelihood, what is your confidence of your estimate? Now, how confident are you about what you are telling me is the mean that you're telling me, your maximum likelihood estimate? So let's go back to what we had. So we had the maximum likelihood estimate in the 2 GPS problem. We had the maximum likelihood estimate was this quantity, C transpose R minus 1 C quantity inverted C transpose R minus 1y. So this was our maximum likelihood estimate. So the question is, what is the variance of your estimate? And what that means is that you're standing still, and these 2 GPSs are measuring what they're doing, and you're combining these two. And your variance, so they're not going to be constant, right? They're going to change because they're noisy measurements. And you're going to constantly estimate, where am I standing? Where am I standing? And so by saying what is your confidence, what we're saying is that what's the variance of this estimate given that you're at some location X? So we need to find the variance of this quantity. So what is that variance? That's C transpose R minus 1 C minus 1 C transpose R minus 1 times variance of y given that at your location X times the transpose of this, which is R minus 1 C transpose R minus 1 C inverted transposed. So it's the quantity times the variance times the quantity transposed. That's the variance of this random variable. Okay, so look at it. Variance of y given r. Variance of y given x. This is just r. So I can simplify my equation. I get C transpose R minus 1 C transpose times R minus 1 times C transpose R minus 1 C to the minus 1 transpose. So this is the same as this inverted. So that's equal to C transpose R minus 1C minus 1 quantity transpose. But variance is symmetric, which means that this is equal to C transpose R minus 1C inverted. So what is this quantity? Well, variance of the maximum likelihood given X, we computed C transpose R minus 1C, and that was equal to the noise in my first sensor plus the noise in the second sensor, the whole quantity inverted. So look what we're doing here. We're saying that your uncertainty about where you are is going to be less than the individual uncertainties in the measurement. So this quantity here is less than RA and less than RB. So your individual measurements had some noise, RA and RB. When you combine them to get the maximum likelihood estimate, your uncertainty about where you are is going to be less than the uncertainty about any individual measurement, RA and RB. So if you have two sensors, your uncertainty about where you are is less than if you had one sensor. Because when you combine the two things, your variance goes down. And that's another important thing that Ernst and Banks saw. So they not only measured what people were estimating in terms of when they combined the lengths, they also estimated their confidence in what they were estimating. And they showed that their confidence was as the maximum likelihood estimate had predicted, that they were combining the two variances and giving a variance of their estimate that was as this equation predicts. So this led to the thinking that when the brain was estimating things from two sensors, it was combining those two sensors in a probabilistic way to maximize the likelihood. Now, how would the neurons do that? That's another question. All right. Good to have you guys today. I hope you had fun. See you on Thursday.